An electron is moving in a circular orbit of radius r with an angular acceleration alpha. At the center of the orbit is kept a conducting loop of radius r. Okay, the center of the orbit, the conducting loop. The EMF induced in the smaller loop due to the motion of electron. Okay, fine. This is complicated. So, what do you know? The magnetic field because of a moving charge. How is that calculated? Well, it should be like mu naught upon 4 pi the charge, then it should be the velocity vector cross r vector upon r cubed, I think. Yeah, it's supposed to be upon r cubed in this case, because you got this r, so magnitude is inversely proportional to r squared, and this should be like that. Yeah, sure. So if that's the thing, that's the magnetic field because of this electron. It's like it's orbiting in this orbit, and then there's a small loop like that. And since we are assuming it's small, we can say, okay, fine, you will just think of it like yeah, like the magnetic field through it is almost constant. Just think about it like that. So we can calculate the flux just by calculating the magnetic field at the origin, and that times the area of this small loop. So what's the magnetic field at the origin? Well, it's going to be this thing. So r vector is this vector, then v vector is like that. Sure. And we know that v and r are just perpendicular, so yeah, it's better. So v vector cross r vector, that's going in this direction, so right hand rule, it says that magnetic field is coming out of the plane. So yeah, out of the plane. Fine. Okay, that's nice. So this times of course pi r squared rule is like pi, call this thing capital R. It's supposed to be very small, but capital R squared. All right, cool. So we can cancel this thing out and just say it's this thing, v by r squared. But we also know that v squared by r, that's the centripetal acceleration. Or okay, let's talk about angular acceleration, because that's what we are given, right? Yeah, so angular acceleration, that will be wait, what was it doing? Yeah, so no, wait, something's wrong. V squared by r is centripetal acceleration. The angular acceleration is different altogether. Yeah. Yeah, so it's like it's d omega by dt, which should be, so it's dv by dt upon r. That's our alpha. So dv by dt equal to r alpha, and you can find out v from that. V equal to r alpha t. Okay, cool. And then we're just going to put that over there. Isn't that right? Okay, fine. So what are they saying? Okay, you can find alpha from that. The EMF induced. Oh, okay, fine. So EMF, that means, right, the magnetic field can be, right. So our magnetic field, that's going to be using this formula, mu naught upon 4 pi, then q, it's an electron, so E, then v is just this thing, r alpha t upon r squared, so r squared, and then that times pi r squared. Get this cancel, so it's mu naught E alpha r squared t. Is that right? Mu naught E r squared, that alpha, that t, this r is going to be like this. Okay, cool. So that's our magnetic field. Oh no, that's not the magnetic field, because we wanted what, the flux, right? That's why we multiplied by pi r squared, so it should be of a magnetic flux, and the change in this thing with respect to time, that should be like just this quantity. Yeah, that's nice. So that thing should be like the negative of that thing, basically that should be our integral ETL. So that's like the voltage or the EMF. So mu naught E alpha r squared. Oh, okay, wait a second. Electron is moving with orbit. Okay, so instead of saying small r, you should say capital R. So mu naught E alpha small r squared upon 4 capital R. That is our EMF. Mu naught E small r squared upon 4. No, not pi over there because that got cancelled. So just 4r, that should be correct. Okay. Next, a conducting loop of radius r is present in an uniform magnetic field B perpendicular to the plane of the ring. The conducting loop of radius r, okay, is present if radius r varies as a function of time t as. Alright. So you can find out the flux first of all. Our flux will just be pi r squared, right? So pi r squared times, oh sorry, what am I writing? Flux will be pi r squared times magnetic field, right? The EMF induced, that's just going to be d flux upon dt, of course negative of that, but you get it. So it should just be 2 pi r p times dr by dt, which we know is just 1 because it varies like this. So yeah, that's just how it should be. So 2 pi, and we know that r is just r naught plus t times b. Wait a second. Sorry. So yeah, that's our flux. So this is definitely wrong. This is also wrong. Oh wait, this is not the flux. It's like d flux upon dt. That's this thing. Okay, so now clockwise, anti-clockwise, what is happening? So the field is going inside of this thing. Flux is also going inside, and this is how the flux changes, the magnitude of it at least. So yeah, like the flux is increasing. Sure. So if the flux is increasing, then the loop will try to oppose the magnetic field, right? So the loop will try to create its own magnetic field in the opposite direction. That using the right hand rule, that has to be anti-clockwise. Yes. So that's it. Next question. A wire of wire loop is placed in the region of time varying magnetic field, which is oriented orthogonal to the plane of the loop as shown in the figure. It's like this. Okay, the graph shows the region of time varying magnetic field. Fine. The graph shows the magnetic field variation as a function of time. Assume the positive EMF is the one which drives the current in a clockwise direction as seen by the observer in the direction of B. In the direction of B. Oh, okay. So when the eye is over here, right, at that point, the clockwise direction, that's supposed to be positive. Okay, drives the current in that direction. Fine. Which of the following graph best represents the induced EMF as a function of time? Right, fine. So first of all, your magnetic field is increasing steadily, right? So it tries to oppose that. So it should create a field that's like in this direction, and for that it has to do this thing, right? Using the right hand rule, it has to do that, which means it's creating a negative EMF in that case. Isn't that right? Yeah. So first it will be negative, and it will be a constant value. Okay. After that, the magnetic field suddenly doesn't change, so that means no EMF is induced. Okay, and then it starts to drop, so it has to be this one. Yeah. Next question. A long straight wire is parallel to one edge, as in the figure. A long straight wire is parallel to one edge. Okay, if the current in the long wire is, okay, it varies in time as this thing, I equal to I naught e power negative t upon t. What will be the induced EMF in the loop? Current varies like this. What's the okay, what will the induced EMF in the loop? This is going to be complicated, because once they have given us all these dimensions, we cannot make any assumptions, so we have to integrate and stuff. Fine, so we'll just find out what's the magnetic field because of this wire at position x. That's going to be mu naught upon 4 pi I, this x distance, I'm missing something. Am I? Oh yeah, of course. That times 2 because yeah, sine alpha plus sine beta. Well, that should be 2. So this is going to be mu naught upon 2 pi x times I. That's the magnetic field. So we just want to integrate this thing. We will say okay, integration of this field mu naught I upon 2 pi x times our area element, which will be b dx, right? And it goes from d to d plus a, I think. Yeah, looks good. Looks good. So it's gonna have natural log and stuff. So it's gonna be what? Mu naught I p upon 2 pi natural log of x, and like it is to be supposed to be like this. Okay, d plus a upon d. Isn't that right? So that is the flux, right? Yeah. And then we just want the induced emf, so it varies like what? So just take a time derivative of this thing. So it should be mu naught I is this thing, so mu naught I naught e power negative t upon t, but then that negative 1 upon t goes on the front, so it's supposed to be that, right? Wait a second. Oh yeah, so there's supposed to be that negative as well. It's like, just talk about the magnitude, it should be like this thing. And also there is a negative sign in the formula, so yeah. Okay, that's nice. So 2 pi tau mu naught I naught, what? It's not supposed to be I. Huh. Oh yeah, so this thing, it's I. That makes sense. So mu naught I upon 2 pi tau, and whatever this thing is, natural log of t plus a upon a. So upon a or d? Upon d, right? Because it starts with d. Yeah, which means this should be this thing. Yeah, that looks right. Next question. A rectangular loop with sliding connector of length 10 centimeter, right, is situated in uniform magnetic field perpendicular to plane of loop. The magnetic inductor is 0.1 Tesla. Wait, what? Magnetic induction. Okay, magnitude of the field is 0.1 Tesla, and the resistance of the connector is 1 ohm. Oh, okay. The sides A, B, and C, D have resistance 2 and 3. Find the current in the connector during its motion with constant velocity. Oh, constant velocity. Well, that's nice. So, you know what the flux changes in this thing is going to be? What's it? It's just this length. We don't know what its length is. It's 10 centimeter. Okay, fine. Just write this down. Length is 10 centimeter, which is 0.1 in SI units. The magnetic induction, that's 0.1 in SI units. 2 ohm and 3 ohm, those are the resistors, right? Okay. Our R value is 1 ohm. Okay, fine. Wait a second. Find the current. Right, so yeah, the change in the area, that's gonna be what? This length times the dx element it moves. So it's dx is just v dt, so it should be L v dt. That's the area change, that times the magnetic field. Yeah, that's right. And then remove this dt, so that gives us the rate, of course. So this is the rate of change of flux with respect to time, right? So this should just be the voltage, we can say that. Yeah, the voltage, the potential difference, it's complicated. So that's 2 times, just say this is I1 and this is I2, so I'm gonna assume it's like okay, this sign conventions, stuff like that over there. Yeah, so this is going in that direction. The magnetic flux in this is it's increasing, so it will try to decrease it, so the current will go in this direction. right? So we will say, okay, fine, you got I1 in that direction, and let's just say that I2 is in that direction, right? So you can say, fine, BLV, the flux change, that should be this 200 resistors times I1, so like 2 I1, and then what's the potential drop in this thing? Is R is 1, so plus 1, and the current is I1 minus I2. Yeah, that's like it. And for the second one, it should be negative BLV equal to 3I2. Yeah, that looks nice. 3I2 plus 1 into I2 minus I1, right? Writing it, you know what, it's not that bad, we can solve this. So B times L, that's going to be 0.01 times V we don't know, right? In constant velocity, current in the connector. All right. Oh, okay, velocity 1 meter per second. So we know what V is just 1 in SI units. Fine. So like, okay, 0.01 equal to, let's solve this should be 3I1 minus I2, and you have negative 0.01 equal to 4I2 minus I1, right? Cool. Yeah, that looks nice. So you can just say, fine, like I1 is equal to 4I2 plus 0.01, and put that in this. So it should be 0.01 equal to 3 times that, which is 12I2 plus 0.03 minus I2, so that's 11I2. Huh, that's a negative value. Okay, fine, if it's negative, it's negative. So 11I2 equal to negative 0.02. I2 is negative 0. And what we want, find the current in the connector. So this R thing, so we want I1 minus I2 or I2 minus I1. So it's 0.02 upon 11, of course in negative, and just put that in this formula for I1. So our I1 is 4 times this, which is negative 0.08 upon 11 plus 0.01. That should be, well, 11 minus 8, that's 0, that's 3, so 0.03 upon 11. And now what do we want? We want, say, I1 minus I2, that should be 0.05 upon 11. That looks nice, which is like what, 5 upon 1100, which is 1 upon 220. Looks right. Okay, next question. A wire shaped as a parabola is located in uniform magnetic field of inductance B, the vector B being perpendicular to the plane xy. Alright, at the moment t equal to 0, connector starts translating from the parabola apex with constant acceleration. Okay, what? Huh. Perpendicular. Okay, that's nice. It's not rotating or anything. Moment t equal to 0, it starts translating from the parabola apex with a constant acceleration. So omega is the acceleration. That's bad. To find the EMF of find the EMF of the electromagnetic induction in the loop this formed as a function of y. Bad writing. So it's probably saying, okay, fine, if this is moving in that direction and there's flux that's changing, magnetic field is going in this plane, then just find the EMF induced in the loop, and I suppose it means this loop. Okay, cool. So how is the area changing? The change in area, well, that's going to be this small area upon time dt, right? What's this area really? It's just x times dy, but like 2 times of that. So 2x dy, yeah, upon dt. that is the dA by dt thing, but we know that y equal to x squared, so like 2x, wait, no, y equal to what, like y equal to ax squared, so that times 2ax times dx by dt. Wait, but we just want, yeah, we don't want it in terms of, yeah, better to just write it as y. So x is going to be like square root of y upon a, and then dy by dt. Dy by dt is just the velocity, call this velocity v, and since it's going with what, that acceleration, just say it's omega t. Wait, but t is gone, of course. Wait, no, it should be there, it should be there. Oh shit, sorry, no, that's not what I want. Yeah, that's better. So where were we? Right, this is our dA by dt, 2x dy by dt. Yeah, which should be 2 square root of y upon a omega t. Alright, cool. So that times the magnetic field, so it should be 2b. Yeah, that's our yeah, that's the flux change, which is also the EMF, which is v. So it should be 2b. Oh, by the way, since it's going like with omega, we can just say, okay, fine, y is it starts at what position, it from the parabola apex. So initially y is 0, and then it's half at squared, I should say half omega t squared. Just put that over there. 2b square root of omega upon 2a, and then that t goes outside. It should be like this thing. Yeah, good. And then we don't want in terms of y. Okay, fine. So our aim is to eliminate this t variable. So t squared equal to 2y upon omega. Just put that over there. 2b square root of y upon a omega, and then t is just this thing, 2y upon omega. So it's 2b, and then that's like square root of omega over there, and this is y, so square root of 2 omega upon a times y. That's good. So 2by square root of 2 omega upon a. Yeah, that's the first option. Next question. A closed planar wire loop of area A and arbitrary shape is placed in a uniform magnetic field B with its plane perpendicular to magnetic field. Resistance of wire loop R. resistance is of resistance of the wire loop is R. Loop is now turned upside down by 180 degrees so that its plane again becomes parallel to the magnetic field. Okay, the total charge that must have flowed through the wire in this process. Total charge must have flowed. Fine. So we find what the voltage is at any given moment. Wait a second. Think. Say if this, like, initially it was just horizontal, whatever this loop was. For simplicity, just assume it's a square loop. So it was like this, magnetic field was going, let's say, into it, and then we change it. So from the top it was just a line, and then we change it, so it now becomes like this. So what happened is that this theta angle, yeah, we change it by this angle theta, and then we just want this theta to become like what, 180 degrees. Cool. So our d flux upon dt, that is what's this thing, is the magnetic field times the area vector, the change in that with respect to time, of course, like d by dt, and at this theta, so the magnetic field is going inside, the area vector is like this, and we want the what, the dot product of these, right? Isn't that right? Sorry. So flux, that's supposed to be the dot product. Yeah. What's the angle between these things? This is angle theta. That's 90 degree. That's wait. Wait a second. What's this angle? This is 90 minus theta. And this complete thing is 90 degrees. So it should be 180 minus theta. Yeah. That's right. 180 minus theta. Because of course this angle is theta. Yeah, that's more like it. So that's not a problematic thing. And we just talk about magnitudes, So magnetic field, the area, and this is like what, sine theta? No, we want the dot product, so it should be cosine theta, I think. And just put a negative sign. Okay, whatever, just think about magnitude, so it should be like pa sine theta. Yeah, that's the change in flux upon. Okay, fine, that's like the potential difference. No, there's no potential, that's just the emf. So p and v upon r, that will give us the current. Okay, and the integration of that with respect to time, that will give us the thing that we want. Oh, by the way, there should also be d theta by dt. Hey, if we gonna do that, why don't we just directly do this thing, that this is the voltage or emf, and yeah, that's the current. And now we can just integrate this with respect to time. R stays a constant, so I equal to b a r cosine theta, and goes from what to what, from 0 to 180 degrees. That's right. Oh, we should not say I, it should be q, because integration I dt, that's q. So just magnitude, right? Just the magnitude of this thing. So 2pa upon r, that's the charge that had to go. So it's equal to 2 ep upon r. Okay, a straight coil ABCD is placed in XY plane with its center at the origin. Straight coil ABCD is placed with its center at the origin. Okay, a long straight wire passing through the origin carries the current. Current in this wire increases with time. The induced current in the coil. What? Induced current in the coil. Okay. Fine. Long straight wire passing through the origin. Negative z direction. Wait, what? Where is the positive z direction? Oh, this should be like what? It should be the positive z direction or the direction of the current. I think it's the direction of the current, because z is generally like what, x, y, and then right hand thumb. So this should be z, and then this should be negative z. So yeah, that's like the current direction. Anyway, so it's going inside. Okay, and it increases with time. The induced current in the coil. That looks weird. You know what, this is not the best way, because like the flux through this thing is always just zero, because if there's a wire that's going like this inside, at any point over here the magnetic field will just be in the plane, right? And the area vector is normal to the plane, so the dot product is just zero. So it's just all the time it's just zero, so it's zero current. Yeah, the induced current in the coil is zero. That's good. Okay, a vertical bar magnet is dropped from position on the axis of a fixed metallic coil as shown in the figure. The figure 2, the magnet is fixed in. Okay, fine. A1 and A2 respectively then. This is weird. I don't think like magnetic field can do that much effect. It should majorly be the weight. No, wait, no. Okay, like it could be that the forces are the same and then the masses are different, something like that. We didn't get the masses, so I'm gonna assume like, okay, bar magnet has more mass and this coil has less. Cool. So yeah, whatever forces are between the bar magnet and the coil, they are mutual. So like if there's force F in that direction, there's force F in this direction. In both the cases the force are supposed to be the same, because like, yeah, Lorentz force, it's it's invariant of the frame of reference, and according to that the forces should be the same because it's the exact same scenario. Yeah, it would be if like they would be the same mass or something, but assuming that they are of these different masses, we can say like, okay, fine, the force on this guy, it provides less acceleration, so it should fall more easily and this should fall less easy. Yeah, a1 bigger than a2, that should be right, I think. Both should be less than g, I think so. Yeah. Oh wait, we just want to say if they are less than g or not. Ah, yeah, both are less than g because they don't want the flux through them to change, so they just like want to stay wherever they are right now. It can only be less, it cannot be more. Okay, next question. A long straight conductor is placed along the axis of a circular coil of radius r. A long straight conductor is placed along the axis of a circular coil of radius r. Okay, like this is the coil and this is the conductor. If the current as shown in the figure, okay, starts decreasing with time, the current in the induced, okay, in the loop, there is no induced loop. Why don't you get it? There will be no induced, okay, there will be no induced current because the flux through this plane is just zero. So yeah, I think that's right. Okay, next question. In a long hollow vertical metal pipe, a magnet is dropped. During its fall, the acceleration of the magnet. Oh, all right. So this is the pipe and there's a magnet in it and it's dropped, so it's wanting to go with some velocity. So you can just think of this pipe as like having, just think about an element over here. It's a bar magnet, so we can say fine, it's got a north south pole, there's some field through it, it's got some flux. As it gets closer, this flux starts to increase, so there's a response, it creates something to, yeah, it creates opposing north pole, so north in that direction. So for that, the current, it has to flow like this. Yeah, and then there's the Lorentz force, so the current is going like that. Of course, if it's like a north pole like this, these are going to repel each other, and that's why it wants to stay like that. Yeah, cool. And since it's dependent on the rate of change of flux, right, that's what the current is dependent on. We can say higher the velocity, more is this force, right? So it definitely cannot just go to infinity. And same thing over here, it doesn't want to let it go because the flux through this thing is also like what, increasing. It's a south pole over there, flux. Yeah, wait a second, I don't know. Here the flux was okay, this in this case the south pole is nearer, so the flux is like negative. Wait, shouldn't we first of all fix the area vector and then talk about it? Yeah, so like the magnetic field, it's going inside it, okay, that's how it is. And then this intensity is getting less as it's moving, so it wants to keep it the same. That's why it will create a field like this, and for that it has to be a north pole over there, a south pole over there. Wait, what? But no, that's not right. If it's getting less, oh, it wants to make it big in that case, so it has to be like this, a north pole in that direction, so it actually attracts this thing. Yeah, that means, oops. And of course, higher the velocity, more will this thing happen. I don't want to get into calculation of all this thing because I basically just don't know how to calculate this terminal velocity. Someday I will. Okay, so we know it will yeah, as velocity increases, this resistance also increases, so it will decrease. Okay, the acceleration of the magnet will decrease to 0 at some point. So will decrease linearly, will decrease up to a value which is less than g. Yeah, it will attain a terminal speed. May increase or decrease, not so sure about that. The arrangement shown in the figure, current from A to B is increasing in magnitude. Okay, induced current in the loop, fine. Okay, fine. So it's normal to this loop all the time, and it's increasing, so the field at every point is also increasing proportional to the current. That means the flux is increasing proportional to the current, right? So yeah, that should make sense. If it's creating, okay, so in the right hand rule we know that field lines are coming out of this thing, so it will try to oppose that and create a north pole inside of the plane. That means, right, so for that, once again using the right hand rule, it has to go like this. That's how the current should be, so it will be clockwise. So the current in the loop will have clockwise direction. Not that bad, right? Yeah, that's nice. Okay, and electric current I1 can flow either direction through loop 1 and induced current I2 in loop 2. Huh? What's this either? Can flow, oh, in either direction. So like this or like this. Fine. Positive I1 is when current is from A to B, okay, in loop 1, and positive I2 is when the current is from C to D in loop 2. Fine. In an experiment, the graph of I2 against time t is shown. So I2 stays constant. Which of the following graph would have caused I2 to be? Right, so if this is constant, that means that flux through it is changing at a constant rate. Yeah, of course. That means that the current through loop 1 is varying linearly. That's it. That's what it is. Oh, there's also direction. So it's positive. That means it's going like this. So using the right hand rule, we can say it's creating a north pole in this direction. Shit. Right. If it's doing that, that must mean that he's trying to oppose something. So this thing should be creating like field. It should be increasing the field in this direction, right? When can that happen? If it's having a north pole in that direction and this north pole is just getting stronger and stronger. So that means that the current should be like this. Yeah, that's right. That's how it should be. So it's going from B to A, but it's also increasing, which means it's negative and increasing in magnitude constantly. So it should be this one, I think. Yeah, that looks right. Figure shows a bar magnet and a long straight wire W carrying a current into the plane of paper. Bar magnet and a straight wire carrying current into the plane of paper. Okay. Point P is the point of intersection of axis of magnet and fine. Which of the following statements is correct? Magnet experiences a torque. Magnet experiences a torque. In anti-clockwise, clockwise. Magnet experiences a force. Let's talk about that first of all. So it's going inside, and according to that right hand rule we can say that this is the magnetic field in that direction. The same magnitude magnetic field is in this direction, but it's a north pole, so the force is in that direction, but over here the force is in the opposite direction. So yeah, like the forces add up to something like this, I think, right? Yeah, that makes sense, I guess. Of course, so it experiences a force in that direction, and there's no torque because these two forces, well, they cancel each other's like, wait, yeah, they cancel each other's torque. So that looks cool. There's no torque, that's just a force normal to the, no, not along the line. Yeah. Okay, next question. A negative charge is given to a non-conducting loop and the loop is rotated in the plane of paper. Negative charge to non-conducting loop. This loop, okay. Yeah. Essential as shown in the figure. The magnetic field produced by the ring affects a small magnet placed about the ring in the same plane. Right. Magnet does not rotate. Magnet. Okay, fine. Let's talk about how it should be. So it's a negative charge and it's going in that direction. So you can say, okay, fine, the current is going in this direction. So that means it's a north pole coming out. So like that, and south pole going in. That should make sense. So, or it will try to align itself. So this south pole will try to move like this, and this north pole will go behind and try to do this thing. Yeah. So as viewed from what? Oh, so from above you can say that the north is going, yeah, it's like it's going anti-clockwise, right? Yeah. So it's anti-clockwise as seen from above. No, not below. So from below it's definitely just clockwise. Yeah. Alright, cool. That's nice. Now what? Next question. Two infinitely long conducting parallel rays are connected through a capacitor C, as shown in the figure. Okay. So magnetic field is going in. It's moving V naught. Fine. Which of the following graph truly depicts the variation of current through the conductor with time? Yeah, this is another complicated one. So what do you know about, because of Faraday's law, you have integration EdL. So I'm gonna consider this clockwise thing to be our L because magnetic field is going inside, that's why, right? So our area vector will also point inside, right? So we know it's supposed to be negative d flux upon dt. In this case, integration dl, yeah, EdL, as we move like this, say it has positive charge q and negative charge q like this, then the field is going to go, we are assuming it's positive, right? So it's going to go in that direction, so it's going to be q by c. Yeah, that's right. That's cool. That's equal to negative d flux by dt. So flux is just the area of this thing times the magnetic field, of course. So negative b and L V naught, that should be right. Yeah, that looks right. That's the flux change. Right. Cool. Resistances, anything? No, we We're not even talking about that. Huh. Right, so at some point it will just like it will get fully charged and it will just stop. That should be doing it. There should be some kind of resistance in these wires, but you know that it's gonna stop. Like this EMF and this EMF, they will cancel each other out at some point. Yeah, when your charge will become that much. So we know the current has to become zero at some point. Well, at t equal to 0, I don't think it's 0. uh no, current can't stay constant. It's not right. It cannot be like this. It cannot be a positive value at infinity. It has to be 0. So only this looks like the correct option. Yeah, that's right. That should be it. Okay, next. Two identical conductors P and Q are placed on two frictional rails and S in a uniform magnetic field directed onto the plane. Identical conductors P and Q are placed on two frictionless rails R and S, uniform magnetic field, directed into the plane. Okay, cool. If P is moved in the direction shown in the figure with a constant speed, then rod Q. Okay. So P is moved like that. What happens to rod Q? This is complicated. These are conductors and frictionless rails. Like, are these rails conducting or not? And these are like very long, I think. Yeah, because yeah, it should be like these are very long. I don't get it. Like, okay, I get it, this that this area should not increase and stuff, but uh wait a second, bro. It will try to stay like that. That's all we know. But how can we even, like, what's the reason that it gets pulled? There's no current or anything. Charges, maybe? It could be. Yeah, sure. Like, if you got like positive charge over there, and then there will be equal and opposite negative charge over there, and the forces will cancel each other out from both of these sides. Yeah, like the torque will cancel each other out, force will still be there, so these will get pulled together. Sure. So this P will experience a force in that direction, but Q will experience a force in that direction, that according to it. So I'm gonna say rod Q will be attracted towards P. Figure shows an isosceles triangle wire frame with apex angle equal to pi by 2. Apex angle equal to pi by 2. The frame starts entering into the region of uniform magnetic field with constant velocity. Okay, the longest side is perpendicular to the direction of velocity. Current, I is the current. Okay. Fine, no big deal. So we know that in dt the dx will be constant. So like velocity is constant, so dx by dt is constant. So for the same dx, you have a bigger y at a bigger t value, which means your magnetic field, sorry, the flux change will be more, so higher emf, right? That means higher current. Cool. So your current will start to increase as it gets even deep. So it will start to increase, and then it will suddenly cut off and just be constant at some point. Yeah. Oh well, okay, in both of these you have increasing. Okay, fine, fine, fine. How is the EMF changing? It is like linear or what? Oh, it should be this thing, I think. Yeah, the current will be linearly increasing, because look at this similar triangles. That means the more this length is, the more of this is already inside it, more will this be length. That means more will be the small area change in time dt. That means more will be the EMF. It's all proportional, linearly proportional. That means it's going to be linear. Okay, next. A long metal bar of 30 centimeter length is aligned along a north-south line. Okay, long metal bar of length 30 centimeter, 0.3. Okay, it's a long north-south line. Oh, so the north-south line of Earth. Okay, so it's like this. This is Earth. You got north, south over there somewhere, and this guy is like somewhere on the diameter, and it's aligned along this line. It's a long metal bar. Okay, so if this is like a small assume it's like a small dipole. Yeah, so the field is going something like this. So at this point we know it's like that. Of course, you just assume it's like on the equator. That means it's horizontal, so it's along the north-south line. That means the field through it is like this. Yeah, and it moves eastward, so it moves like this at a speed of something meter per second. A uniform magnetic field of 4 Tesla points vertically downwards. Vertically downwards. Wait, what? Points vertically downwards. Oh, so like, okay, fine. So it's going in that direction. If the south end of the bar has a potential of 0 volt, then the induced potential at the north end of the bar will be. We can calculate the magnitude, and it's probably just 12, but the direction is what matters at this point. So it's along the north south. What north south? Is this magnetic north south, or when you say the south end, we should mean like the direction south end, right? So the south end will in that case be this one, right? So magnetic field is going in like this. This is the south end. It has 0 potential. What's the potential of this thing? Isn't that what you're saying? And this is east. This is the south. The what do we say, like what we refer to as the south direction. That's that thing. And this is north, right? And it's the magnetic north as well, and that's east. Okay, and it's going down towards it, right? So if that's 0 potential, then what's the induced potential at the north end of the bar? Yeah, so just think about any small charge in this thing. It's moving in that direction. There's, if you want like some potential, you know what, if this is positive, it will go in that direction, right? So just say that's the field because of this thing, and then there's some force because of the magnetic field, right? Because it has some kind of charge. Yeah, so this is the magnetic field is like going inside. This is the velocity vector, so v times b. Yeah, that looks right. It goes in what direction though? Negative is going down, so v cross b, that should be in this direction. Oh no, that's not nice, because according to that, the field in that case should be going in this direction. That means this is the higher potential and that's the lower potential, so it should be negative 12. Yeah, and why should it just be 12? Because like b times v equal to e. That means like that times length, that's the potential. This v and this v is different, so the length is what, 0.3. the magnetic field is 4, and what's our v value? Of course there's also magnetic field in that direction. Do we have to care about that? Well, I guess we do, because no, not really, not really, because that is going to be in this or this direction and it cannot move in those directions in the first place, so don't care about that. So that will be 0.3 times 4 times our v thing is speed 10 meter per second, right? So it's going to be 12. So magnitude is right, and I think the direction is also right. Next, a square metal loop of side 10 centimeter and resistance 1 ohm is moved with a constant velocity partly inside a magnetic field of, okay, wow. So our magnetic field is 2, resistance is 1, side, call this L, is 0.1. A loop is connected to a network of 5 resistors, each of, yeah, R not, R is 3. Facility current of 1 milliamp, so 10 power negative 3, closing the loop. Then the speed of the loop is, all right, so you know what the current through this thing is, wow, this is complicated. Come on, think about it. Wait a second, we said that all of these resistors, all of these are of 3, right? Hey, that's a balanced with stone bridge, so just remove this thing. So just 3 3 3, so like 6 and 6, that should just be an equivalent resistance of what, 3? That's right. So we can simplify this diagram and say, okay, cool, it's just this thing. You got 3 ohm resistor over there, and this complete resistance is like what, 1 ohm, right? Yeah, so this complete thing is just 1 ohm, which I'll just say, okay, this is like that approximately. So that's nice, right? So we don't know the velocity, we want to figure that out, and we know the current and stuff. Yeah, so B times L times V, that's going to be the flux change. Well, this is the L thing. Yeah, okay. So this is like the potential that upon the total resistance, which is in this case 3 plus 1, right? Because that's 1. Yeah, and that's equal to our current. Magnetic field, we know it's 2, so 2 times the length is 0.1. Potential, we know that? Oh, this is not potential, it's the velocity. We don't know that, of course. So v upon 3 plus 1 equal to I, which is 10 power negative 3. Right, that's cool. So this is going to be 10 power negative 2 over there. So 2 by, that's going to be 2. So v is 2 into 10 power negative 2. Yeah, meter per second, of course. So this is like 2 centimeter per second. Cool. So 20 questions should be enough. Let's just check these. Where is it? This is exercise 3. Where are the answers? Shit. Okay, wait a second. I need to just wait a second. So 20 questions, there we go. Let's go. Okay, first B, second C, third C, fourth B, 5th B, 6th A, 7th C, C C D, C C D, C A D, C did I wait, this is D, okay, this should be A. Why did I did not do it? Okay, anyway, it's A. 14th D, B C A, B C A, 18th D A C. Oh no, this is A and this is C. Okay, this is weird. So it's plus 12. Okay. Fine, I'll look into that. Anyway, that's it for this video. I'll see you in the next one. Bye.